So in this video, we're going to talk about two things. We're going to talk about acceleration and then motion diagrams. And so let's start with acceleration. So acceleration, we've already defined. Acceleration is a change in velocity over time. And that's a vector quantity. So that means that we need to know magnitude and direction. For one-dimensional motion, the direction is just given by the sign, so positive or negative. So to determine it, we take the change in the velocity and we divide it by the change in time. So remember that any change is going to be the final minus the initial. So this would be like the final velocity minus the initial velocity. And then on the bottom, we'll get the same thing, so the change in time, which would be the final time minus the initial time. Now, one note on notation. Typically, we're going to say that the initial time is 0. And so this, because if we're using a stopwatch, this would just go away. It would start at 0. And so we can simplify this and just say, it's the change in velocity divided by the time. And that's usually fine. So how much of the velocity change divided by the time? This, the portion up here on top, the velocity, that's what's going to determine direction. So that will determine whether you have a negative or positive velocity. And so let's, or acceleration rather. So let's look at a couple examples. So we'll do example 1. So a car, let's say, starts from rest, moving to the right, so it's moving this way. The initial velocity is 0, and the final velocity is, 11, and this is meters per second. And then let's say this time that it took, so the initial time is 0, because we always do that, or not always, but most of the time. And the final time was, say, 3 seconds, okay? So it took 3 seconds to do this. What's the acceleration, and in what direction? Because we need both. So in this case, we would just start with our definition. The acceleration is always the change in velocity over time. We can put change in time. And then we can pull that out. So that's our final velocity minus our initial velocity divided by time. And then we plug in our values. So the final velocity is 11 minus the initial velocity 0 over the time, which is 3. So we get 11 divided by 3. And if we calculate that really quickly, it's 3.67. So we get an acceleration of 3.67 meters per second squared. So that's our acceleration. And it's positive, so it's going to the right. So our velocity is to the right, so our acceleration is also to the right. This one was velocity. This was a velocity vector. So let's, I'm going to talk a little bit about motion diagrams, and then we'll do another example with acceleration. So in this case, the object was speeding up, it got faster, and you can see that the acceleration and the velocity are in the same direction. They're in the same direction. And we'll test that. We'll test that in, let's just do that first. Let's test it. So now what I'm going to do is I'm going to turn it around. I'm going to say the car's going the other direction. Example 1. So just to clarify, to the right up here is positive. So now what I'm going to do is I'm going to say the car starts over here on this side. So this is positive direction. So it starts here with an initial velocity of 0, and it's going to move in this direction now. So it goes this way, and it ends up over here with a velocity, a final velocity of 15. Now let's say it does it in the same, let's say it does 5 seconds. So the time final is 5 seconds. Time initial is 0, of course. So the car moves along and goes along here and then ends up here. So now we want to determine the acceleration. So to get acceleration, we just do it again. We always start with the definition or law. That's what we write down first. So in this case, I just want the change in velocity over time. So that would be the final velocity minus the initial velocity. I always write this down because I don't want to get them backwards. And so the final velocity, now because the velocity, let me go back to this picture. The velocity at this point is in this direction. So it's not really 15, it's going to be negative 15. So my mistake, let's correct that. Why is it negative? Because it's going to the left. And I said right was positive. So we have a negative velocity here. Remember, the negative just indicates direction. It's moving to the left. Okay, so we get negative 15. Sorry, let's keep some consistency with colors. So negative 15 minus the initial velocity, which was 0, divided by time. Time is always positive, so 5. And so what we have is we have negative 15 divided by 5, so we see the acceleration is negative 3 meters per second. So up here on my picture, the acceleration is also to the left because it's negative. So what we see here is that when the acceleration, when they were both to the right, the object was speeding up. And when they were both to the left, the object was speeding up. And that's our rule. If acceleration and velocity are in the same direction, then the object is speeding up. This means then. The object is speeding up. Now this is important, and this is a big misconception, because right here, we have a negative acceleration. We have a negative acceleration, and a lot of students might say that it's slowing down because the acceleration is negative, but that's not true. It depends on the direction of the velocity. It depends on the direction of the velocity. So as long as they're in the same direction, if the velocity is negative and the acceleration is negative, it's going to speed up. Or if they're both positive, it's going to speed up. Now we'll just do a quick example of slowing down. So example 3. So now the object, the car starts with a velocity of 20 meters per second. And then it slows down. I'm not going to do 0. It's not going to stop. Let's just slow it down. Its final velocity is 10 meters per second. So the object is slowed down. And let's say this happens over, 10 seconds. Or no, let's do 5 seconds. Oops. So time here would be 0. And then here would be 5 seconds. So now we want to determine the acceleration. So the acceleration, we want the magnitude and direction. So how much and what direction? So the acceleration is the change in velocity over time. That's our definition. And then we just expand it out. So final velocity minus the initial velocity divided by the time. I'm just dropping it because, time is 0. So the final velocity is 10. So we get 10 minus the initial velocity was 20 divided by the time, 5. So here you just have to be careful with signs. 10 minus 20 is negative 10. So we get negative 10 divided by 5, so you get negative 2 meters per second squared. So based on this sign, the acceleration is in the negative direction. So my velocity is to the right in both cases, because that's positive direction. But now my acceleration is opposing it. So the acceleration works against it. And that's slowing down. And this, I'm not going to go through the example because, it should be fairly obvious. If the object is going this way and slowing down, so it's moving this way, and then it slows down. So it goes from, 20 meters per second, or negative 20 meters per second, to negative 10 meters per second, then which way is the acceleration going to be? Well, it's going to be against it. So it's going to be this way. So that's our second rule. This was the first one. If they're in the same direction, it's speeding up. If it's opposite, then the object is slowing down. Okay. So now you've seen how to actually calculate, given the velocity and time, the change in velocity and time, and these two rules. So careful with those. So now we're just going to talk about motion diagrams. I was kind of drawing them here, but we want to specify what they are. So a motion diagram is just a representation of some motion. And what it is it's kind of like a strobe photography, where if you imagine we take a picture of something as it's moving. So let's say, I'm not even going to do a car. Let's just do a ball rolling along a road. Or let's do a car. Okay. So this car has an initial velocity of 5 meters per second in this direction, and then it speeds up to, 15 or something. Doesn't matter. We're not going to calculate anything. Then imagine that we take a picture of this car like every second. So every second, this car, number one, it's speeding up. So since it's getting faster, it's going to cover more distance every 1 second. So like time is 0 here, then it may be here, and then it's going to cover more distance because it's getting faster, and then it gets faster. So we may end up something like this. And so we would see the little car, right at these points, at these times, where that's time is 1, time is 2, time is 3, and so on. And so what we can do is we can just model this with a motion diagram. And so to do that, all we do is draw a circle to represent the object. And we draw a circle because the shape and the size of this don't matter. It could be a car, or a runner, or an elephant, or a ball, or a dog. It doesn't matter. And the motion is what we're concerned with. So we just draw it as a circle. And then we're going to draw vectors. We're going to put vectors on this thing. So just recall, velocity and acceleration are vectors. So that means that they have a magnitude and a direction. So to draw a vector, we use arrows. Because arrows show me both of those. They show me magnitude and direction. The length of the vector, the length of the arrow, is the magnitude. It's how fast or how much. And the arrow itself points in the direction. That one just makes sense. And so we can draw a velocity vector. Well, first we know that it's going to move a little bit, and it's going to be, I'm kind of drawing it from here. So it's going to move a little bit after 1 second. And then after 2 seconds, it covers a little bit more ground. And then at 3 seconds, it's moved a lot. So then we can go back on this and draw our little velocity vectors. And then we label it. So this is velocity. And then the velocity gets longer. And it gets longer because it got faster. And then longer. And longer. So this just represents the motion. Now we can actually add our acceleration. The object is speeding up, so we know the acceleration is in the same direction. So we have acceleration in this direction. And we typically will write it between the two velocities, because it shows like this plus that is this. We'll get to vector addition. And for this class, it's always going to be the same. Well, in certain scenarios, we'll have constant velocity. So we indicate that by showing, the velocity, the acceleration, constant acceleration. The acceleration isn't changing. And this is a motion diagram. So we just got to figure out the direction of the velocity and the acceleration. And we can do that based on whether it's speeding up or slowing down. But that's acceleration and motion diagrams.